Cool. Good morning, everyone. We are Team 7. We're going to be talking to you today about deadlocks. So, what is a deadlock? A deadlock is a set of processes where they're trying to access a set of resources, but the only way to interrupt their accessing the set is through interrupt calls by a process within the same set. So basically you have this infinite loop and you're not really able to get out of it. So here's an example. You might have seen in Windows at some point. Press enter to get out of it, or F1. But you can do that because there's no keyboard. So that's an example. All right. So detection of deadlocks. This is a pretty important piece. We're going to ask ourselves the question: if the system is deadlocked, which processes are involved? Well, there's one way to do this called the ostrich algorithm. It's pretty simple. Basically, just stick your head in the sand and pretend the problem isn't there. It goes away on its own. That'll time out. We can have detection with a single type of resources, where we basically construct this graph. So the squares here are the resources, the circles are the processes, and these arrows are the vectors. And if they form a circle like that, a cycle, then it's not going to be broken and it's going to go on indefinitely unless we do something about it. We can also detect with unique resources or different types of resources where we basically do the same thing, or we can construct this matrix and we can analyze that matrix to figure out where a cycle can be found. And of course, we can also recover from this using rollback to a previous state where we know everything was working properly, or we can just simply terminate the processes and deal with the problem later. So I got a question for you. What's the ostrich algorithm?
You just don't do anything.
Yep, it's pretty simple, right? All right, I'm going to turn it over to Kenny. There you go. And here is Michael Peterson with the next section here.
Okay, so avoidance. The Bankers algorithm was created by the Shocker, Dijkstra, however you pronounce it. And essentially the Bankers algorithm is meant to ensure that the system does not run out of resources. And essentially it does this by three main components. The maximum required resources by a process, its allocated resources, and the total number of available resources on the entire system. It does this by detecting like safe states and unsafe states. So safe state is basically when a process can allocate the maximum number of resources it needs to finish its goal and still finish successfully. So that's a safe state. And then an unsafe state is when there isn't a way for the process to allocate enough resources to finish its task, and thus the Bankers algorithm tries to avoid it, to stop any unsafe states from happening. The limitation of the Bankers algorithm, however, is that the information needed to actually use it effectively, like the process's total maximum resource allocation, is usually not available on the system, and so it's really not used in practice. So this graph basically just illustrates it with the grayed out sections. So I have a question for you. What's a safe state?
It's a scheduling order.
Yes. That's it. And now I will hand it off to Trevor for the prevention.
So there's 4 conditions Kaufman requires to have a deadlock to occur. So to prevent it, couldn't we just block one of those conditions, and that would prevent the deadlock? Well, the first one, mutual exclusion condition, that's when a resource can only be used by one process. We can't prevent it entirely in this respect, but if you avoid assigning a resource and limit the claiming processes so that only one process can use a to limit the number of processes that can use a resource, just limit it. So it helps prevent conflicts. Then you have the hold and wait condition. This is when a process is allowed to hold a resource, and then request another one, and just continuously wait for that to come in. You can have the programmer specify the specific resources that a job will need, and then it's reserved until it finishes. But this puts a burden on the programmer and wastes resources, so not too ideal. Or you can have the requester temporarily release all the resources at once and then bring them all back in, preventing a deadlock to occur because it's not holding on to the resources. The no preemption condition, this is when you can't forcibly remove a resource from a process. You can't just grab it out without that process saying it's okay. And this can be done with some, but not all. So, for example, if you spool the printer output to disk and only allow the printer daemon printer access to the real printer, that would work. The printer would no longer have deadlocks. But it could create one over the disk space. But that also, if you have a large enough disk space, it doesn't matter. And finally, we have the circular wait condition. This is the actual cycle where the processes are asking for the other one's resource. So you have somewhere in your system that cycle that they get stuck. You could limit the process to one resource at a time, but you just can't do that because some processes need more than one resource to function. So that would work for little things. Or you could have a global number for each resource and make it so you can only ask for something that's higher up on the resource chart. So you have this ordered list. So this one can ask for the resource from this one, but this one up here can't go back down the list. It has to go up. So it finishes what it's doing, goes away, then this one can go up and get what it needs. All right, next up, question, yeah. Which one of these techniques can be used to actually prevent deadlocks? Any one of them. No, some of them only help deadlocks. The others actually prevent them entirely. That's the one that only helps. Try again. Any other one?
3 more guesses. Circular wait condition.
Yep, those will prevent deadlocks. And next up, I have Kim with other types of deadlocks.
Okay, so first we're going to talk about communication deadlocks. Communication deadlocks trigger when a set of processes is trying to communicate with each other and no further processes can continue until they receive the communication somebody's waiting for. So if you're sitting out in the hallway and you're trying to talk to somebody and your best friend is trying to talk to somebody, whoever you're trying to talk to can only talk to one of you at a time, so you have to wait until they acknowledge you to talk. These deadlocks cannot be prevented by ordering your resources or avoiding careful scheduling because it's just not going to work because it's only when the resource is available. And so timeouts are the way we break these deadlocks. What happens is when you start a communication, a timer starts, and once that timer runs out, it says, hey, send it again. And it sends it again and again and again until it finally goes through. The only problem is you don't know how many times that message actually went through, and it could have just been stuck, so the sender could get, the receiver could get 7 or 8 of these communications at the same time, and it causes a lot of overlap. So we also have live locks and starvation. A live lock, the easiest way to explain it, because the book explains it in like 7 different uses of the word thread and other process, is trying to sidestep somebody in the hallway. You know how it is. You're walking down the hallway, somebody's walking down the same spot, but you sidestep, and they follow you, and it takes 4 or 5 times for you to realize it's just easier for you to stand still and let the other person go by. These are like deadlocks, but the processes aren't stuck because they're locked. They're stuck because they're too busy trying to respond to each other. They don't stop and go, oh, wait, if I just shut up, then other people can go through it, but they're not smart enough. And starvation is when a thread is unable to gain access to a stored resource. This is easily avoided by using a first come, first served resource allocation policy. What is starvation, people? Come on, you can do it. Have candy. What's a candy?
It's when a thread is unable to gain access to shared resources.
There you go. Oh, wow. Yeah. Wow, girl. And yeah, Aaron, here to wrap it up.
First, we'll start with the video, which is just a brief overview of what a deadlock is in general, with a interesting animation style.
So what is the deadlock problem? The deadlock problem occurs
occurs in transactional databases when there is a set of block transactions, each holding a piece of data and waiting to acquire another piece of data held by another transaction in the set. Basically, two or more transactions wait for each other to unlock data. No transaction can continue until the other transaction has unlocked the data. Here's an example of a deadlock. Both Michael and Matilda want to update a set of two tables that are related, but there's a problem. Since they are accessing the database simultaneously, Michael is updating the table is locked, so no other transaction can access it. When Michael wants to use table B though, he finds it's locked and has to wait. While that's happening, Matilda wants to use the table A. She also finds it locked and also has to wait. Both of them cannot continue with their transactions. So what are the control techniques for the deadlock? Prevention, i.e. hold and wait, no preemption, circular wait. Avoidance, i.e. deadlock avoidance algorithm. And detection, i.e. deadlock detection algorithm, recovery scheme.
That's pretty much it.